Thanks, Nick. What I'm going to talk about is the UK national programme, and every now and again I'll make a reference to what's going on here in the UK as well. The national programme has all sorts of characteristics that distinguish it from other national programmes around the world. And in particular, all the stakeholders are working together with a single board to deliver a strategic vision on it. That's kind of unusual that we got joined up thinking. So all the ones that were initially involved in this are at the bottom of this slide, and some of them, of course, have transformed their name and their logo. So Technology Strategy Board is Innovate UK now. CESG is now the National Cybersecurity Centre. I think, no, Department for Business Innovations and Skills has an E in it now for enterprise. But basically, all of these people engage together to deliver a program on quantum technologies. So what I'm going to do is to say, what's quantum technologies? Well, of course, as you've already heard, we use quantum technologies all the time because that's how a semiconductor works. That's how a laser works. But to some extent, that's old quantum technology. It's stuff that comes from the early days. What's the new stuff? What we're trying to do is to find ways of exploiting two different bits, superposition and entanglement. They're kind of freaky things. And if you try and talk to a business audience, or even worse, HM Treasury, and you start with that, you get nowhere. Okay, because they think, oh yeah, the guy's going to tell us about philosophy. But what we're going to do is exploit these things in devices. All right, so where's the initial investment on the national programme? It came from George Osborne. We had a number of community meetings where we looked at what could be done, who could do it, how they would engage with each other. We had a major workshop to try and focus this. From that workshop, we wrote a piece that went to the science minister. The science minister then says, can I have a 2-page version of this for HM Treasury? And then number 10 said, could we have just it on a single page, please, that I could take it home over the weekend? And what it generated initially was 270 million in the autumn statement of 2013. That's the largest single investment the UK government's ever made in a disruptive technology. That's over a 5-year period. And the aim of it was to translate the really great science that was underway in British universities into things that are going to create wealth and employment and focus on this. So it was right from the outset meant to be an ecosystem which pushed stuff out of the labs into things that people needed to use. Okay? Right. So, how we started. So I mentioned about community workshop. I look after a country house up in North Buckinghamshire for the Royal Society, where we brought all the stakeholders that we could locate. And one of the things about this place called Chichiley is when you get there, there's absolutely nothing to do except talk to each other. Okay? And what we came up with was this kind of plan. And it's now in its 2nd edition. It's got about 200 pages behind it of what all these things are, and it's publicly available. Where we have a journey where some of the things we've been talking about in the discussion period are over here, computing. Okay? But over here, there are things that emerge from that journey which have an immediate relevance. So what we tried to do is to make sure that we had within this journey things that we could pull out involving clocks for precision timing, communications, security, sensors. All of these could be pulled out en route. There's a big vision over here. What I've always said, I used to say that we have 5 years of funding and a 10-year vision. Trevor's heard me say this so many times. It's likely now we have 10 years of funding and a 15-year vision. Okay? Right. And so there we go. How do we spend the money? And this is very busy. You won't see it all, but I'll talk you through it. First thing we did is that we identified these focal areas that are really important to us. Imaging, communications, quantum computing or quantum information processing, and sensing and metrology. And we set up 4 hubs to deliver on these things. Now, at the same time as setting up the hubs, the training and skills exercise, the innovation program by which we could work as partners with companies, that's the part that's growing. The National Physical Laboratory set up a Quantum Metrology Institute, and Patrick, where's Patrick gone? Patrick is the co-director. I chair the board, and NPL is an essential partner in all of this. And then there are other investments, but basically you can see that we're trying to involve the whole ecosystem from training and skills right through to engagement with companies. This little tiny slab down there in Quantira, that's our little seed cord money of working with the rest of Europe. Okay? And that's all spent now. Right, okay, so last year we have these things called Blackett reviews. It's nothing to do with the fact that I used to be the head of the Blackett laboratory. Okay? Blackett was one of the pioneers of science-based advice to government, operational research in particular during the Second World War. And so we have these Blackett reviews, and last year Mark Wolpert and I produced this one. It's called The Quantum Age. It's out there on the web, and it's designed for policymakers to understand what goes in this area into ways in which we can make a difference to people's lives. Okay. As soon as we did that, doors start to open elsewhere. Okay, so whenever anybody they go back to think, what was I told when I was a student about quantum? You get molecular orbitals. That's not what we do. We're trying to work out ways in which we could build devices, chips, things that are really going to be useful in prototypes. Okay? So manufacturing of things that are relevant. And so when I do talk to Treasury, and I talk to number 10, we don't really talk about the entanglement and the superpositions. We talk about accurate financial trading, sensitive subsurface sensing, secure information protecting. And in each of these, quantum technology is transformational, as you've heard from a number of people earlier this afternoon. For example, in subsurface sensing, half the holes dug up in London are in the wrong place because we don't know where the buried infrastructure is. We are spending billions on subsurface sensing. Think about brownfield sites that had to be cleared. Okay? Quantum sensors really have that ability to map the unseen world. Okay? Securing our information, we've already talked a lot about that, about how and I'm going to say a few more words about it. Right, now you didn't get Ed Hines because Ed isn't very well, so I thought I'd better say something about cold atoms. Cold atoms are an ingredient to this program, and by cold I mean incredibly cold. I mean much colder than the 3 degrees that Mark was talking about. Okay? We're talking about nanokelvin. And the way we do that is by laser cooling. And it's a little bit like slowing down a bus by throwing snowballs at it. Okay? You need a lot of snowballs to slow down a bus. Well, to slow down an atom, you need a lot of photons. You throw at it, and eventually you slow it right down. Okay? And as soon as you do that, they start to exhibit these funny wave-like properties that are of value to us. You can get interference, you can build interferometers, and from that, you can build accelerometers and gyros that are starting to look as alternatives to the MEMS things that Tom was describing. Okay, so there are things that are underway on that, and you can see from the bottom slide that the early adopters of that are the Ministry of Defence. The Ministry of Defence have put 35 million for the prototype devices that we're doing, and they also funded 42 PhD students around the country to see this stuff through. Right. So what do you use them for? Well, holes in the ground, mine shafts, and so on. So we've called these projects the Quantum Navigator and the Quantum Compass. Okay, and they do have lots of opportunities. I've just mentioned about the cold atom version, but of course Tom has just shown you a MEMS version which doesn't need cryogenics and is fantastically sensitive. And because it was space qualified, doesn't eat up power and doesn't weigh a ton. Okay, So, lots of stuff you can do. Now, one of the things that we also are working quite hard on is some of the timing stuff. Okay, I've already said all of that lot. But clocks are really important to us. And it's been the first application of quantum technology. The fact that you run your GPS system for navigating is because there are atomic clocks that utilize coherence. They use this spin precession coherence. That's actually one of the first ever applications of quantum superpositions, and it's transformed our lives. Okay? Right, I'll come back to that in a moment. The way that we define time almost certainly will be transformed with iron clocks that Patrick is the world expert in, lattice clocks and so on, which are going to be transformational. These are primary clocks as well as the compact miniature ones. Okay, so GPS. You have this constellation. We are fantastically vulnerable to GPS. Think about those satellites. They're a bloody long way away. So the power that gets to your receiver is tiny. Okay? It's so easy to jam or spoof. Okay? So there is a new Blackett report on GNSS, in other words, GPS vulnerabilities. I was going to say it's out. I've had the proofs for weeks and weeks now, but it's actually stuck with number 10. We want to approve it on GPS vulnerabilities. Okay, I think number 10 has got other things to worry about at the moment. But this is important because we all use it in geolocation. Okay, but lots of other things we use it for. Okay, so we can build all these devices using quantum stuff. Okay, we can build clocks. Clocks. Why are clocks important? Well, because a little atomic spin, it precesses around, you isolate it, and it's really fantastically accurate. If you bring that spin next to something, that little precession frequency will change. That's one of the bugbears in trying to build a quantum computer. It's influenced by its environment. What a pain. All right, turn the argument on its head. That pain becomes your advantage when you're building a sensor, because it couples so extraordinarily well to the environment. Okay, so we can build magnetometers and so on. So one of our deliverables, one day within the national program, is to build a brain sensor which looks like a cycle helmet. Okay, no cryogenics, just optically pumped, little tiny, well, like miniature atomic clocks basically, on your head, does the brain imaging for you. No need to shove you through a damn great scanner. Okay, it will happen. For cold atoms, we can do a whole raft more. Okay, so these are kind of the deliverables that we talked about. I'm going to talk a little bit about encryption. How do you do classical encryption at the moment? You've got a sender, Alice, and a receiver, Bob. You've got an eavesdropper over here. And what you do is you take your plain text and you transform it with a secret key. Okay? And the receiver better have the same key. Okay? This is a really simple way of doing crypt. All right, and because the eavesdropper doesn't have that key, can't undo whatever the encryption was. And what we do know is that quantum both is a threat and an advantage. So again, from the back, I think you can't see these things, but there are various encryption algorithms up here. DES, AES, RSA, and one-time pads. Now, you're all smart people. You know perfectly well that the only absolutely secure encryption is a one-time pad. Yeah? Shannon proved that. It's also totally unfeasible to use, okay? Because the key length has to be the same length as the message, okay? Well, but you can imagine one-time pads could be used for high-value stuff. All right. So, let's see what happens when the adversary has capabilities that are quantum enabled. Well, even classically enabled with massive classical. Firstly, DES is dead. DES is dead because of classical computation advances. All right, so what about AES? AES, that's now vulnerable because you can now use quantum protocols to attack AES. RSA, You've already heard from Mario. That's vulnerable. This one isn't. Okay? So, the ability to actually run stuff out from here to there when you've got an adversary with either massive computational power or quantum resources is now at risk. Now this is, yeah, I'll skip these. Oh, no, I won't skip that one. That's important. So quantum cryptography gives you the ability to do secure communication using the laws of quantum mechanics, and it's been used in kind of surprising ways. It was used to secure the cantonal elections in Geneva. Wasn't sure where the threat was there, but anyway, ID Quantique secured them. Many of you know about the Meteor satellite, the Chinese satellite that was used to exchange quantum information to and fro. Okay, and satellite comms secure is actually the trick by which we can take the stuff that can run on a metro network, quantum secure, to another metro network via space. Because space isn't that far up. You know, there's not much there. So attenuation is not really very important. All right. Now, you can build things that a theoretical physicist says, gee, it's secure by the laws of quantum mechanics. But it isn't, because it's hardware. And hardware is operated by people who are sometimes incredibly stupid. And they lead to roots. So the inappropriate use of hardware leads to vulnerabilities. So what we've got to do is to investigate whether or not the systems we're going to be deploying have really been analysed into their vulnerabilities. All right, so we've heard this already. Richard Feynman, the great hero, says, simulating, quantum advantage. I do want to mention David Deutsch, who came up with the first proper algorithms that show quantum advantage. I've known David for probably 40 years. I've never seen him in daylight. Does anybody else here know David? Mario, you must have met him.
I'm not sure, actually.
Take a flash lamp. Right, so quantum computers. Right down here we have hardware, and it could be, there's a number of platforms that we could use that we've heard a bit about. Then we have to do error correction. And then once we've done all that lot, what are we going to do about programming it? What are the algorithms that are going to run it? So that's the ecosystem for quantum computing. IBM have a superconducting platform which you will be able to access on the web fairly soon. Small scale, but it's a test. Microsoft have put all of their money, big time money, into one particular realization that's called topological quantum computation. It's a hell of a risk. And the reason they're doing it is that you can do it without this layer, if they get it right. But it's a hell of a punt. Okay. Right, so the crypto apocalypse, because I do want to get onto this one. The word crypto apocalypse hugely annoys GCHQ. Okay? So that's a really good reason for using it. Okay. Information security and e-commerce, all the things that we kind of used to in the way that we now trade, inform ourselves, pay for stuff and so on, is based on hard problems. And by hard problems, I mean they're based on the use of NP problems that are not NP. So if that's gone past you already, don't worry. Okay? But for example, factoring is really hard. Proving you've got the factors is dead easy because it's multiplication and it's only polynomial in resource. Okay. And of course, everybody said, well, that way, we know factoring is hard. All we need to do is increase the size of the big numbers we're using in RSA, and it's always going to be secure. But what Peter Shaw showed is that what was going to be exponentially hard becomes polynomially easy. Okay? And that's the threat. So when we talk about quantum safe encryption, with the new lattice-based systems, close vectors, all the rest of it, who knows if there's another smart character like Peter Shaw who will find another route in. So vulnerability analysis is important. Okay? Information security is tough. And so here at Imperial, we've already heard about this collaboration between physics and electrical engineering on this post-quantum world. Okay. This slide, I think, should be the take-home message for most boards. Do we need to worry? Okay? And so I love to call this thing, I call this thing the Moskva Equation, because Michele Moskva is my academic grandson who came up with the idea, and he hates the label. How long do you need your cryptographic keys to be secure? That's your shelf life. Let's call it X. How much time will it take to retool the existing infrastructure with a quantum safe solution? Let's call it Y. That's the migration time. How long will it take for a large-scale quantum computer to be built? Okay, let's call it Z. That's the collapse time for your protocols. If X plus Y is greater than Z, then worry. That's the Moskva Equation. All right, should we worry? What are these timescales? I think we should. We shouldn't panic, but it's now we should worry, because I believe the quantum computer threat is of the order of a decade, and the rollout time, the migration time for quantum safe, is going to be of the order of a decade. Okay? So you're getting really close to this worry stage. And I think every single company that has come to rely on HTTPS needs to know that there is this. Okay? That's the big picture one. All right, so I'll skip all of that. Okay, quantum computing. To execute a factoring algorithm is going to require a very large number of quantum bits. Okay, so let's not get carried away. I think that what we'll be able to do fairly soon is to get hundreds of qubits fairly soon. Okay, all right, so a Manhattan scale project will actually accelerate the process of getting to the big stuff. The Chinese, in their 5-year plan, have announced a multi-billion investment in quantum computing platforms. That's the Manhattan scale. Okay. There is something odd about this, though. If you have 50 qubits under proper control, as Mario was sort of hinting at, you can't simulate it. You run out of space. That was Feynman's point. So where are the algorithms that exploit this quantum advantage? You know, we can't model anything bigger than 50, and the big algorithms involve 1 million. Where are the applications between 1 million and 50 that we can use? Simulation, looking at drug discovery. So the Prime Minister, before she got distracted, asked me for a societal challenge that quantum could address. And I said, right, I had about a minute's notice to think of this one. So I rather unwisely said, protein folding. Why? A third of the population of the country will suffer from diseases generated by the misfolding of proteins. It's the underlying cause of dementia. If you try to model protein folding, it's computation. It's not a quantum problem. It's just you run out of space when you're trying to compute it. So if you want a societal challenge that's going to be really important, I would love to see medics, polymer scientists, density functional theory people, and the quantum algorithm people come together and have a crack at this to see if we can understand this formation of this misfolded polymers that turn into plaquettes. Okay? Right. And I think I can get very close. Oh, yeah. The rest of the world, we've heard about that. Google, Intel, IBM, Lockheed Martin, you name it. Okay, there's people everywhere. This is almost my final slide. Okay. So we started with a national strategy for this thing after all these workshops that we had. There's a copy, it's quite short. And it was fueled initially by looking at GPS and timing vulnerabilities, especially in fintech. Automatic trades really were the thing that got me excited about fast trades. Precision timing and navigation project, we got people together in Chichely. We came up with the demonstrator projects. We had this national injection. The size of the national program now is 385 million, and we've got another 16 months to burn it, okay? So we're in the middle of negotiating the second phase. Part of that was we updated the landscape about what the capabilities were. We generated the Blackett report on opportunities, okay? Two things then happened. I'm responsible for the vision piece for phase 2, working with my colleagues, Trevor is one of them, on how we can deliver this thing. The other part of it is the Innovate UK through the Industrial Strategy Challenge Fund. Okay, now some of you won't know what the hell it is, but on Monday, the white paper on industrial strategy was published. I wished it was only that short. It is one of the most tedious reads you'll ever have. But if you look very closely at it, there's lots of stuff in here about disruptive technology. So one of the things we were able to do, announced on Monday, is that they've given us another 20 million to build consortia of industry-led people to look at where we could go next with this new technology. And one of the people that really was instrumental in getting a focused bid on this was Anki, who's over there, who gave me this next slide, which is really my last one. Okay. Underpinning all the stuff we do in the UK is photonics. Okay? Photonics is one of the secret jewels of the UK economy. It generates more to the GDP of the UK than pharmaceuticals. Who knew that? Well, some of you did, because I've been banging on about it for about a year. Okay? But it's in 1,500 companies. It's got a very complex ecosystem, okay? But, and this is why Treasury gets animated by it. Treasury is really worried about the stalling of the productivity of the UK workforce, okay? The GVA, the gross value added per employee in the photonics sector is 3 times the national average. That is really important. 75% of its output is export driven, okay? Anki insisted that it said 5%. It used to be 8%, didn't it?
We looked at the numbers.
Yeah, okay. So you've got this massive secret industry. Why don't you know about it? Because it's part of the supply chain that feeds all the other sectors, okay? And of course, when you talk to Innovate UK, they are rather obsessed by sector-based industry, okay? We actually are enabling the huge range of sectors to use the new technology. So that Niels, where's Niels gone? Niels' company is generating a very large amount of productivity and employment in the UK on efficient lasers and other systems that are addressing this. Now, I guess your export ratio is roughly this, 75. It's 85%. That's M squared, based up in Scotland. So, that's the bottom line. What can quantum do for us? It's the enabler to do things that you couldn't do before. We believe you can do it at a price which is affordable. That's really important. You can't, it will replace things that are on the shelf. It can be transformative. So the three things I want you to take away. Underpinning it is one of the big success stories of the UK. There you are. Secondly, what we will do is enable you to see the invisible. These are the buzzwords we've been using. Seeing the invisible, building sensors, and securing our information. Thank you for listening.